Good morning, everyone. Welcome to the first talk session this morning on separation logic, and our first talk will be given by Paulo.
Thank you very much for this introduction. Can everybody hear me? No. Should I wait for the mic to work? Is it working now? Can you hear me?
No, I think it's working, but it's just very low.
Okay, can you somehow increase the volume of the mic? Can you hear me now? Better?
Can you get Eric's mic?
Sorry?
Eric's microphone?
Yeah, we're just using this.
So, okay, I will remove this one then.
I think so. Is that okay?
Yep. So you can hear me now? Yes. Okay, thank you very much. Thank you very much for the introduction. This is joint work with Simcha von Collem, Ines Wright, and Robbert Krebbers. And I would like to start by saying what's the goal of this work. And in simple words, is to design a relational separation logic for effect handlers. And I imagine that when reading this goal, two questions come to mind. What is a relational separation logic, and why design one for effect handlers? So a relational separation logic, like any program logic, is the given of two things: an assertion language to specify programs and a set of proof rules to verify programs compositionally. And the key feature of relational separation logic is the ability to reason about to compare the behaviors of two programs. And specifically, in relational separation logic, we can assert that the program on the right-hand side, on the specification side, is a correct abstraction of the program on the left-hand side, on the implementation side. And more formally, what this means is that every terminating behavior of the program on the implementation side is a terminating behavior of the program on the right-hand side. If it terminates with a value, the program on the specification side terminates with a value, and they're related by, these values are related by the postcondition. Now, why design a relational separation logic? Well, there are many interesting applications of relational separation logic, and here I'm listing only three. The first one is to verify programs and to reason about programs using simpler implementations as specifications. A second application is on compiler optimizations, and namely to show that a compiler optimization is correct by showing that the optimized program does not introduce behaviors, to use the source program as a specification of the optimized program. And a third application is to show both soundness and abstraction properties of type systems. Now, to show why relational separation logic is relevant for effect handlers, I'm going to focus on this application, on program verification and program reasoning. And I would like to discuss an example of effect handlers, and namely the fork effect, an implementation of the fork effect. And what we can think about this program is that it's implementing a scheduler for multiple currently executing tasks. All these tasks are suspended and stored in a queue, with the exception of one whose execution is monitored by a handler. When this running task performs a fork effect, the handler takes the continuation, which is a representation of the suspended task, and inserts this task in the queue, the continuation in the queue, and immediately starts running this new task. At the end of running this task, the handler will check for continuations in the queue, and if there's any, it will resume the continuation. So in my opinion, this is a very elegant implementation, also very concise, but it's also very hard to reason about because it uses advanced programming features, such as dynamically allocated mutable state and first-class continuations. So with relational separation logic, we can, in fact, abstract this whole program into one single line, where this fork functionality is simply given by a native fork instruction. And this statement also helps us to understand a fork effect as actually a native fork instruction. But it also reveals some problems, some difficulties in formalizing this statement, because here we are reasoning about a fork effect in isolation of its handler. And the issue is that an effect only has meaning under a handler. Its meaning depends on a handler. And this issue is going to come up in 3 challenges to design a relational separation logic for handlers. The first one is into how to specify programs, because if we look at the standard refinement relation in relational separation logic, it does not talk about effects. It only talks about terminating behaviors with values. So implicitly, there's the assumption that when we use this refinement relation, there are no effects on the implementation side. A second challenge is how to allow compositional reasoning about handlers and handlers. So we would like to decompose the verification of a program with a handler into the verification of the handler and the verification of the program that performs effects. And to illustrate, if we want to verify the program I just showed, the statement, the relational statement I just showed before, at some point we would have to reason about the composition of a handler and the handler. And at this point, we would like to split the proof into a handler part and a handler part. And we can see here that, again, we come up with this problem of having to reason about a program that performs effects in isolation of a handler. And more generally, we would also like to the logic to enjoy some context-local reasoning principles, such as the reasoning principle allowed by the bind rule in standard relational separation logic, which allows us to, when verifying a pair of programs under a pair of contexts, to focus the verification into this pair of programs. And the question is, can we allow a similar rule in the presence of effects? So the key idea of our work is to come up with a new notion of refinement in the logic. And our idea is to parameterize refinement relation with a theory, which can be seen as an axiomatization of the relations that should hold. And this resulting logic, it's called base, and it's built on top of Iris. So the way we formalize a theory in Iris is by means of this function that takes as input a possible refinement between 2 expressions and a postcondition, and returns what is the condition for this refinement to hold. And what I would like to stress here as well is that nothing mandates that this theory talk about effects. Actually, these are arbitrary expressions. And this is important to give the logic the flexibility to allow us to relate effects with programs that are not effects. To give some examples, to make this more concrete, the simplest example of a theory would be the empty theory, where to refinement, the condition for this refinement to hold is simply false, meaning that there are no possible admitted refinement by this theory. If we instantiate the empty theory with our parameterized refinement relation, we recover the usual refinement relation in relational separation logic. A slightly more involved example would be that for fork effects. And here the question is, what would be the condition for a fork effect to be related to a native fork instruction with a postcondition R? And the condition is actually a conjunction of 2 conditions. The first one saying that the tasks should be related, and the second one saying that the postcondition should hold for the result of these operations, which are both unit. And using this theory, we can formalize the intuition I gave in the beginning of the talk, that a fork effect refines a native fork instruction under the assumption that the fork tasks are in a relation as well. So now we're going to revisit the challenges I listed before, the 3 challenges I listed before, and see how this new idea of a refinement, parameterized refinement relation would help us to solve these challenges. And the first challenge was that given that the meaning of an effect depends on a handler, how can we give specifications to programs using, how can we define a refinement relation that gives meaning to programs that perform effects. And here the idea is to rely on this technique from the literature called B-orthogonality, which essentially means that under the hood, we're always talking about some universally quantified context. So under the hood, the definition of a parameterized refinement relation will quantify over context and state that these pair of programs are in a relation using the standard refinement relation of separation logic under universally quantified pair of contexts. And to establish this refinement, we have the assumption that this pair of contexts they validate the relational theory. And what it means to validate the relational theory, it means that if we plug related values to these contexts, we obtain related programs, and if we plug related expressions, we obtain also related expressions admitted by the theory, we also obtain related programs. So the way we solved the second challenge, which was the compositional reasoning for handler and handlee, is by means of this exhaustion rule, which for the verification of a pair of programs under a pair of contexts, it splits the verification into the verification of the expressions themselves and a condition on the contexts. And what is important to note here is that when applying this rule, the user has to come up with a theory to carry on with the proof of the refinement between the expressions. And what the condition on the contexts means is that the context, again, validate this theory. And it's very similar, actually, to the definition of the refinement, with only the difference that here we also allow the statement for the refinement between the contexts. It also allows a theory for its F for itself. And what I would also like to notice again is that these contexts, nothing mandates in this rule that these contexts contain handlers. And again, this gives the flexibility in the logic that when applying this rule, there could be a handler on the left-hand side, but no handler on the right-hand side, and vice versa. So, what I would like to also highlight is that this rule kind of enforces the idea that the theory is an abstraction on the eyes of the program that performs the effects of the handler, and for the handler is an abstraction of the program that performs the effects. And finally, the logic also allows a principle for context local reasoning with the naturally extension where we annotate the refinement statements with a theory. And it contains, the only difference is that it also contains a condition that this theory be traversable. And one intuition is that it allows us to commute a theory with a pair of contexts. And another intuition is that a theory is traversable for a pair of contexts if it holds regardless of this pair of contexts. And that's what it allows for this rule to be sound, and to when we focus on this pair of expressions, we can ignore this pair of contexts and still have this theory. So I'm not going to give the definition of what traversable is, but what I can say is that not all theories are traversable. But thankfully, the logic has a mechanism to make theories traversable by construction. So again, I'm not going to give the definition of what a context closure of a theory is, but I'm going to characterize it through two properties. The first property being that the context closure of a theory extends a theory, meaning that every refinement that's valid and that is admitted in the theory, original theory, is also admitted in the context closure. And a second property is that the traversable condition on a context-closed theory simplifies into a conjunction of syntactic conditions on the contexts. And what this syntactic condition means is that there are no handlers in these contexts for effects in this set, but there could be handlers for effects not in this set. And when we instantiate the bind rule with a context-closed theory, we obtain a version of the bind rule where we exchange the traversable condition for syntactic conditions on the contexts. Now we're going to revisit the example from the beginning of the talk and see what there are key ideas to verify this example. So there are three key ideas. The first one is that we must come up with a theory to reason about these fork effects. And not surprisingly, the theory is going to be the one I showed before, the theory about fork effects. But we're also going to take the context closure of this theory. And with two sets, the set on the left-hand side is going to be the singleton set with fork effect, because it's the only effect in this program. And on the right-hand side, it's going to be the empty set, because this program doesn't have effect. And the second step is going to be to apply the exhaustion rule to decompose the proof between a proof of the handler and a proof of the handler. And what the handler part will look like will be this refinement. And in this refinement, we're going to use the bind rule to focus on these, on the perform effect, on the perform fork effect, and on the fork instructions, and then rely on the theory to prove to finish the proof on these specific atoms. And for the verification of the handler, it happens that we could not use the standard relational separation logic to reason about concurrency in this program for a very simple limitation that in most previous relational separation logics, we could not reason about the case in which the fork instruction in both of the programs do not match. And that's clearly the case in the program I just showed before, because there are no forks in the left-hand side. So we have to come up with three novel reasoning rules for concurrency, which are independent of effect handlers. And I'm not going to go super in detail into these rules, but I'm going to give you an idea of what their use looks like in the verification of the program I just showed. And to do that, I'm going to use this box where on the bottom we have the goal, the refinement we want to show, without the theory and without the postcondition, just to simplify. And on the top of this dashed line, we're going to have the goal. So the rule for R, we're going to need it to reason about the case in which the program on the left performs a fork effect, and the program on the right is about to call the native fork instruction. And what this rule is going to allow us to do, this is a case that previous relational logics wouldn't allow, because there's not necessarily a fork on the left. And what this rule will allow us to do is to introduce this resource called a thread pool resource, which tells us that on the right-hand side, there is a thread with identifier I that is executing the program, this task. Now expanding this, the handler branch, we're going to have two instructions, an update to the queue and the run. So in the proof, we're going to have an invariant for the queue, in which every continuation in the queue, for every continuation in the queue, there's going to be a thread on the right-hand side with which this continuation is in a relation. And so we're going to need a thread pool assertion for this thread on the right with which the continuation is in a relation. But this is not the thread on the right with which the continuation is in a relation. The thread on the right is actually this, the one on the right side of the judgment. So we need somehow to obtain the thread pool assertion for this program. And what this rule allows us to do is to exchange these thread pool assertions to obtain one describing the main thread on the right. And now we can update the queue, maintaining the invariant, and the rest of the proof just carry us on with an inductive argument. And finally, we have to verify the return branch, and at this point, we're going to pop a continuation from the queue and re-obtain a thread pool assertion for some thread on the right with which the continuation is in a relation. And what now this rule will allow us to do is to allows us to think of this program on the left-hand side as if it was being forked, and use the assertion that they are in a relation to finish the proof. So to conclude, in this talk, I showed you the importance of relational separation logic for program verification and program reasoning, specifically with the fork effect. And the main challenge coming from this issue that the meaning of an effect depends on a handler. And I show you the base logic, which is built on top of Iris, with the novel idea of refinement relation parameterized by a theory. I showed you that base allows compositional reasoning about handling and handling, and also context local reasoning. And I showed you that we introduced novel reasoning rules for concurrency that are independent of effect handlers. And in the paper, there is much more. Actually, what I show is base, and implicitly, I was always talking about static effects, but there's also a logic, a whole other logic in the paper for dynamic effects built on top of base. There's also a discussion about deep and shallow handlers, to which both these logics have support, and also one-shot and multi-shot considerations, again, to which both logics have support. And we also have many other interesting case studies, namely some refinements between asynchronous programming libraries and a handler correctness criteria in Blaze for algebraic effects for non-determinism. Thank you very much, and I'm glad to take questions.
So there's an interesting difference between the theories you're presenting here and the notion of protocol you've used in previous work on program logics for effect handlers.
Notion of what? Notion of what, sorry?
Of protocols.
There is,
And specifically, I wanted to ask that they're now parameterized over expressions instead of values.
Yeah, exactly, yeah.
And I wanted to ask whether that could also give interesting reasoning principles for unary logics as well.
That's a good question. So, yeah, so two obvious differences. One you mentioned, these are expressions. So in protocols from the Hazel logic, they were always values, meaning that we always have to reason about specific effect instructions. And another difference, obvious difference, is that this is binary and not unary. And the question is whether this gives you some intuitions for unary case. And to start with the definition of the refinement relation, we could think about a definition of a unary logic where we don't, so in the Hazel logic, we had a custom-made weakest precondition. So in this logic, we don't need, we can always rely on the traditional refinement relation of the logic. So that would be one idea to improve on the unary case. And another idea, I think we could also have a more flexible bind rule, which is not really related here to unary or binary case. It's kind of independent, but which actually relies on these being expressions rather than values.
Okay, thank you.
No problem.
Sorry, could you? One more quick question.
Hi. Thanks for the talk. Can you go to the next slide, actually? Slide 15, I think.
Sorry?
The next slide, slide 15. Yes, so you have this, this context closure operator, and now you have this traversable equivalent to this syntactic property.
Yeah.
Is it equivalence or is it one direction?
It's equivalent.
It's equivalent.
In this case, it's equivalent.
So, but your traversal property, is that a syntactic property or a semantic property?
It's a semantic property.
Okay.
Yeah,
So
it's defined semantically, but in this case, in the specific case of a context closure, these are equal.
Okay. Yes. Thanks.
Take further questions offline, and thank Paulo.